Welcome back to the meadow map. Look at this right-cornered garden plot. If a fox wants to get to the other side, cutting straight across the diagonal path is shorter than walking the two outside edges. But exactly how much shorter? To figure that out, we can look at the sides of the path as physical spaces. Let's build a square garden extending outward from each of the three edges of this right triangle. We can observe a direct relationship here. The total land area of the two smaller square gardens perfectly equals the area of the single large square on the diagonal. Translating the theorem into a relationship of physical areas turns a memorized string of algebra into reasoned knowledge about right triangles. You can see exactly how the space around the shape behaves. Let's test this area relationship with some concrete numbers. Here is a new triangle plot with side lengths measuring exactly 3, 4, and 5. We'll start by looking at the shortest leg, which is 3. If we build a square off this side, its area is 3 squared, giving us 9 square units of space. Now for the second leg, with a length of 4. A square built here has an area of 4 squared, which is exactly 16 square units. Finally, we check the longest side, the hypotenuse, measuring 5. If we take the 9 units from the first square and the 16 units from the second, they combine to make exactly 25. The arithmetic backs up what we saw visually. The physical areas of the two squares on the legs will always add up to the area of the square on the hypotenuse. We can also prove this relationship using pure logic, without measuring specific lengths. Take a look at these two large, identical square garden beds. Inside the first bed, we have placed 4 identical right triangle stone pavers. The way they are arranged leaves 2 smaller, separate squares of empty soil. Let's label their areas A squared and B squared. Think about this for a second. If the outer borders of the garden beds are exactly the same size, and the 4 stone triangles never change, what must be true about the leftover soil in the second bed? Now look at the second garden bed. We took those exact same 4 stone triangles and pushed them to the edges. This new arrangement leaves one single large square of empty space in the center, which we will call C squared. Because the total garden area is identical in both beds, and we used the exact same 4 stone triangles in each, the amount of empty soil has to be equal. The 2 smaller squares of soil from the first bed mathematically equal the single large square of soil in the second. We can also run this logic in reverse. Here is a completely unclassified triangular dirt path with side lengths of 5, 12, and 13. We need to find out if the corner where the 2 shorter paths meet is a true right angle. To do that, we isolate the longest side. Since 13 is the largest number, this side is our possible hypotenuse. We check the math by squaring the lengths of the 2 shorter legs. 5 squared is 25, and 12 squared is 144. When we add those together, we get a total area of 169. Next, we square the length of that longest side. 13 squared is also 169. Because 169 equals 169, the squared side lengths balance perfectly. That means the angle directly opposite the longest side is mathematically forced to be a right angle. The central relationship holds. The squares on the legs add to the square on the hypotenuse. Before we wrap up, take a moment to think about this question. Why do the leg squares' areas add to the hypotenuse square's area? Mastering how this visual proof and its converse work prepares you to take this geometric rule out into the real world, where you can use it to calculate actual missing distances.